So, good morning, everyone. Let me wait for people to slowly come in. Yeah, they are slowly coming. I'd like to make two invitations for you guys and for me as well. One sort of a sad one and a happy one. The sad one is the following. Let us remember our brothers and sisters in this earthquake, horrible earthquake in Turkey and Syria. And let's direct, I'm not asking for 1 minute of silence because we don't have 1 minute of silence, but let us, just at this moment, direct our thoughts to our brothers and sisters that lost their lives, their houses, their everything in Turkey and in Syria. Okay? Just for 1 little moment. Thank you. So now the happy invitation, I'd like to invite you all to, we announced that by email. There is, Juliana Bueno Soler and myself, we recorded a course on argumentation, on critical thinking in Portuguese, which is available in this Coursera website, and it's completely free, around 20 hours of lectures. It's in Portuguese, and we have already more than 10,000 people following this course. It is very important in Brazil at this moment because we almost entered the domain of irrationality in our fascist government, which fortunately is finished now, has its roots still working in subterranean. And this course is very, very important for us at the moment because it's sort of restoring our capacity of arguing in a civilized way. Okay? So I'd like everyone to follow that. It's in Portuguese. If there is enough interest, we could make some subtitles in English. But that depends on how many people that cannot read Portuguese will follow it. People that understand Spanish can follow it because it's written and it's slowly spoken, and you can be following if you know Spanish, right? So I'd like to invite you to follow that. Its address is already sent, has been already sent in your email. So today I will finish the course which is started with João Marcos, and so I'll be speaking about consistent evidence and probability, mixing these two topics. So the overview will be on consistent logic, that I don't need to say anything else about this topic here because you are already completely colonized by paraconsistency, I would say. Contradiction as conflict evidence. This is something new. The logic is as I call logic of evidence and truth. J and F, based on intuitionistic logic and on this Bell-Naplan logic, extending to let F, valuation semantics, some facts about let F, and applications. I am very much excited to mix probability with non-classical logic, with something other people already started. Graham Priest did something years and years ago. He gave some suggestions. Edwin Maris gave some other suggestions, but I'm following a different path. So I'd like to show you how we can really mix logics and probability in a very useful way, which I think is very much interesting and very much applicable or applicable. Okay. Okay, so paraconsistent, I don't need to remind you, is the investigation of a logical system with a non-equivalent negation. That is a negation, that it's not the case that every pair of propositions implies average. Okay? Then, in paraconsistent logic, in our way of doing paraconsistent logic, we change this principle of explosion by the principle of gentle explosions, as already explained. Then, contradictions as conflict evidence is something which is important to be explained here. For a consistent logic can be concerned with a notion weaker than truth that allows an intuitive understanding of a contradiction. I mean, it's not that we say there are no dialectias in the world. We just don't need to talk about dialectia, okay? Because contradictions appear maybe in dialectias, but they also appear in databases, in information, in language, in dreams, in thoughts, etc., etc., etc. Okay? And some evidence is an epistemic also related to the justification of proposition, but evidence may be contradictory as well as incomplete, thus demanding a paracomplete and paraconsistent one. This is an epistemic and non-dialectic approach to paraconsistency. Now, why is evidence so important? Because evidence is what lies behind the philosophy of science, lies behind justice, investigations in justice, in law, for instance, or in many other kinds of investigation. You look for evidence for or against something, and then we give you more and more evidence, you get close to the truth. Huh? At a certain point, but also, before anything, evidence can be contradictory. I can have a contradictory evidence. That happens all the time. Evidence can be missing. For some topics, I don't have any evidence, neither for or against. Right? And also, when I collect more evidence, I may go towards discharging that my first belief or justifying it and concluding something. When I conclude something based on accumulation of evidence, then we say we are close to the truth. And then we declare we have the truth. We have arrived at the truth position, right? Like in a judgment, like in a court. So you make a bunch of people, give them lots of information, and they arrive at a conclusion, they decide that the person is guilty or innocent. Is this the truth? Is this a metaphysical truth? I don't know, but it's considered to be conclusive. So, for practical purposes, conclusive evidence can be regarded as truth, either in the court or in philosophy of science. That's the way science works, right? For momentarily, I have good evidence for the theory for Darwinism, for the theory of evolution, then I consider it true. That's the way we work, okay? The notion of evidence that is true is to be understood as reason for believing in or accepting the truth of A, and evidence that A is false, reason for believing in or accepting that false in false of A. So positive evidence is independence from negative evidence. There are four possible scenarios that we can start with. One is A holds, there is evidence that A is true. A does not hold, there is no evidence that A is true. Not A holds, there is evidence that A is false, and A does not hold. There is no evidence that A is false. Okay? So in previous papers, we developed another logic, the BLE, the basic logic evidence, and G, that J is the logic of this true based on intuitionistic logic. Semantic for such logics are available, etc. But I had a relevant question here, is whether the amount of evidence available for A could be quantified. So we not only are adjoining or augmenting the evidence on something, but giving some degree to it, right? And then we use the probabilistic semantics to give degree. Well, we could give, for instance, we could think about fuzzy systems, fuzziness, or even the theory of possibilistic logic, like possibilistic measures. But we prefer to start with probability because there's more mathematics connected to probability, much more mathematics than to other topics, like in fuzzy system, fuzzy logic is there are mathematical treatment, but I think that probability has more. Okay, so I will show here a probabilistic semantic for a more sophisticated logic. This LET or let F. This logic is an extension of the logic of first degree entailment, FDE. Then it's a logic of evidence through based on FDE. Another logic extending FDE is 84 or BLE, obtained by adding a semi-intuitionistic implication to FDE. So starting from this first degree entailment, there are several, maybe at least two ways to extend this logic. One is adjoining to it this intuitionistic implication, and another one is the way we do making it to be talking about truth.
Oh,
Yeah.
let me just add quickly, because you put N4. N4 ends for Nelson.
N
We
for
were
Nelson.
talking about this before. You reinvented this logic with a good reason, because the motivation was to have intuitionistic-like approach to evidence, and also for the absence of evidence of the falsity. And so in a very natural way, you reinvented this logic. And it's known that actually the super well-known logics are actually a continuum number of logics in between FDE and classical
I didn't know that.
logic. This was proved by Humberto Ligeti.
Apparently, there are more logics than people in the world. So for the consistent preservation of it, then the logic to be a lead and let so BLE, this is paracomplete and paraconsistent, equivalent to Nelson's 84. For instance, it does not hold in this BLE or 84. B implies A or not A or not A implies B, A or not A, not A, B, blah, blah, blah. BLE is adequate and decidable with respect to the bivalent semantics. The meaning of the formula of BLE in terms of preservation of evidence are given by a composition of inferential semantics, as we prove it. But anyway, my topic here is not really BLE, it's going to be let F, okay? So here we have a proof theory for BLE or N4, which is something red. You see it's very symmetrical. There is a normal symmetry in terms of proof theory, but that's important for people that are interested in proof theory. It's not my topic here. What's important, and I don't want, because I have lots of slides, that's why I'm just jumping and going to the important ones. And then this FDE is the well-known and widely studied well-known using for-valued logic, right? So rather remind that FDE is like BLE without implication. FDE deals with inferences. A entails B, where A and B are formulas forming only with conjunctive, disjunction, and negation. FDE has neither theorems nor bottom particles. Has no theorems at all, nor bottom particles. Is paraconsistent, paracomplete. And this is an important point when you're talking about the evidence, because as I said, just repeating, evidence can be contradictory and can be missing. So I really need a paraconsistent and paracomplete paradigmatic approach if you want to understand evidence. Then evaluation semantic, decision procedure, and inferential semantic for providing for BLE, the only small changes to be applied to FDE. The FDE is very respectable, very much studied, nice logic. And then, again, there is a very symmetrical proof theory in terms of natural deduction for FDE. Just reminding that FDE, BLE without implication. But then, why we moved from BLE to FDE? The moving from BLE to FDE has been motivated by two main reasons. The difficulty in providing a plausible and intuitive reading for the intuitionistic conditional, and the fact that the FDE works as well as BLE with preservation of it. Well, what we need here, I'm going towards the following objective. Talking about the evidence, and talking about the preservation of evidence, and talking about conclusive evidence. So there is a move here from FDE, blah, blah, blah. So this, they're very much symmetric. Because of the symmetry, there are several points in proof theory that you can arrange for these logics. I'm not interested at this moment. There is this famous inversion principle, which shows that if you work very well with introduction rules, you don't need to work with elimination rules. So they are sort of so symmetrical. None of them implies the other one, the other half. But those are very, very specific points of proof theory. Now, let's go to LEF, logic of evidence in truth based on FD. So this is interpreted in terms of the preservation of evidence. BLE as well as FD is not able to express truth preservation. There is no mean to express the stronger claim that the proposition A has been established as true or false. Since in the framework of BLE or FD, an assertion means only that there is non-conclusive evidence. So as I said, I want to go towards conclusive evidence. And regarding conclusive evidence as true. As the trueness, in other words. If you add to BLE or FDE some means to restore the validity of explosion and exclude the middle with respect to classical formula, we recover classical logic. So classical logic holds with respect to propositions we want to assert as true or false. What is our mean in talking about recovery? By the way, recovering is the topic of our course, right? So recover the truth means if everything is consistent, coherent, if I have this white ball in front of all my assertions, I get back to classical logic. So I'm not destroying classical logic, I'm just expanding, not exploding classical logic. I'm giving some more material to it.
Walter?
Yeah.
Just a quick question. Can you interpret like preservation of course not truth, but like something like at least true? Can you read it like at least true?
Well, you could, but that's an interpretation. I mean, you can also say momentarily true, for the moment it is true. You can, but you don't need it.
Yeah.
That's your choice.
Walter, once I heard when you were presenting some of the systems, and you mentioned that there was some relation between one of them and a previous system introduced by Lopes Escobar. Is one of these, of those?
Yes.
Which one?
BLE.
Yeah.
Yeah.
When it was introduced by Lopes Escobar? I don't remember.
Years
quite
and
well.
years ago, I think it's some 15. I
But
don't
it's
have it.
it's the same system.
Not the same, the equivalent, right?
Okay.
That's what happens to logic. There are so many logics that they
Yeah.
coincide each other.
Yeah, because
As I said, there are more
confused.
logic than people in the world. There are more logic than cows in the world.
Yeah, I was a little confused. So, thank you.
Okay, thank you. So this notion of evidence is weaker than truth and can be missing or contradictory. The notion of a computer being told that Belknap and Michael then proposed it is related to evidence, a notion weaker than truth, since a computer may be told that alpha is true and it's not the case. So Michael then, in 1976, also explains the occurrence of simultaneous truths of alpha and not alpha. It says, do not get me wrong, I'm not claiming that there are sentences which are in fact both true and false. I merely point out that there are plenty of situations where we suppose, assert, believe, etc., contradictory sentences to be true, and we therefore need a semantics which expresses it. So that's exactly your point, right? So the world of information, of language, of dreams, of the thoughts, of the judgments, of discussions, of the argumentation, they can have contradictory movements and missing points, and that's why we need as it says, a semantic expression. So extending FDE to let F, a logical for evidence in truth. So FDE is not able to talk about truth. FDE cannot distinguish a context where alpha holds and not alpha does not hold, but alpha is not true, from another context where only alpha holds because it's true, right? So it's not able to express this subtle distinction, which is very much important when we are making an investigation, when we are talking about philosophy of science, when they are applying your Bayesian epistemology in order to revise your beliefs by giving new evidence. Okay? So the extended logic lab F is able then to distinguish these contests. So here, this consistency alpha means there is conclusive evidence for or against the alpha. We also say that then the alpha is classicized. Because when I arrive, when the judgment jury arrives at the conclusion, everything was confused by a certain time, but then the point has been classicized. It means I have arrived into a sort of a Boolean or classical situation. Not classical as Priest explained it in the sense of the Greeks, but classical in the sense of the 19th century philosophers that invented that term. So in black, inconsistency alpha means there is no conclusive evidence. Okay? So then F is obtained by adding the following inference rules. Everything is okay up to this point, but now I'm adding two very important little rules. If the alpha is classical or consistent, and alpha and not alpha, this implies every possible meaning. This is again the gentle principle of the explosion in action here, right? That João Marcos mentioned many times. Gentle principle of explosion. And this one here says, if I get from A and not A, if I get B, then I get B. So I'm restoring this tertiary non-data here, in the presence of this consistency. So the intended meaning of consistency A is that classical logic holds for A. So the truth and falsity of A can be expressed respectively by what is something to be true. It is consistent and it is the case, and false means it is consistent and it is not the case. Or you can read again, it's conclusive and it is the case, or it's conclusive and it's not the case.
Oh,
yeah.
We just had, because the first part of the course, the second rule that there makes it a determinedness connective. Consistency connective on the right, on the left, and on the right, it's a determinedness.
Determinedness.
So in your logic, the square is collapsed.
Yes. So those guys appear in the famous square of everything that João Marcos presented. It's not a square of position.
You don't have four connectors.
Yeah.
That's what's important. You collapse into two. That's what I want to point out.
Yes.
You don't need to do that collapse, but you do. Okay?
But it can be.
Yes, you can.
Yeah.
Like you can read this as evidence.
Yes. So the operator consistent may be understood as context switch. So if I have a consist of A, consist of B, consist of C, if all of them hold together, then the argumentation context of A, B, C, blah, blah, blah is classical. So if you want to stay on the classical side, you just reason with consistent objects or conclusive objects in terms of evidence. Then you will restore your classical reason. Then you can apply Boolean logic, Boolean thinking, the Boolean thought. These following rules can be derived, can be proved, and like that. So if I have alpha and not alpha, then I have alpha is inconsistent. But not vice versa. This is an important, conceptual point in our approach. So contradiction implies inconsistent. But inconsistent is something much bigger than contradiction. Inconsistent is dissonance, non-harmonicness. Can I say that? Non-harmonicness. Like sounds that are not harmonic between themselves. They are not contradictory. They are not sounding well. They are not coherent. So contradiction is something which is linguistic. I can recognize a contradiction. If I have a sign for negation, something A and not A, alpha and not alpha, is contradictory, saying something contrary. This is just one part of inconsistency. Inconsistency is much bigger. So you can ask me, what is inconsistency then? I don't know. It's some kind of human phenomena, rational phenomena, which encompasses everything which is not good enough. Incoherent, non-harmonic, blah, 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 blah. Whatever you don't like, you put on inconsistency, right? So that's why inconsistency does not imply contradiction, but just vice versa. Well, you can make them together. You can establish that, okay, inconsistency is the same as contradiction for me. Okay, you can do, no problem. You are getting in this way closer and closer to classical reasoning. It does not restore classical reasoning because of that. We have other logic, João, Marcos and I have been working on Delphi 1, for instance, and others, where this connection is made, and the logic does not get classical, it only gets closer to classical. Okay? This is, I think it's an important philosophical or conceptual point.
She has a question.
Yes? Sorry. Okay.
If I ask it now, because later, like, I may not have the chance to, so is it okay if I ask the question now?
Yes, if I can hear you, it's okay.
Okay. So I was just wondering, regarding the consistency operator, the circle. What are the rules, for introducing this operator? Do we have, what are natural deduction rules that are connected to this operator?
Yes.
Can I just see them on the slides?
Goes here.
Okay, so we don't have any other rules?
No.
We don't have rules on how to introduce this?
No.
No.
You know why?
Yeah, why?
Why?
Yeah.
Because consistent he's not a subject of logic. You never introduce anything because of big logic. Consistent is something that comes from an external world. It's an external information. Yeah?
Okay.
That's an important point.
Yeah.
So there is no, as Kripke used to say, there is no substitute for philosophy. Not even logic. Okay, then you have this you can derive those rules. Then it's possible, as I said, I repeat it here, to prove that contradiction implies inconsistent. However, the order direction does not hold. This can be seen by the decision procedure of the semantics, but the simple fact it has a deep philosophical meaning in the sense that inconsistency of alpha has a broader scope than contradiction. What is contradictory is inconsistent, but not vice versa. That is important to understand that point, because many people don't get that, don't grasp that point, and that makes our system not valid for them, because they don't see that one. Now, sake of dissonant musical chords, mismatched color, or any form of disharmony, discordance, incongruence, incompatibility. These are inconsistent if it's black alpha or inconsistent alpha, but not contradictory. I mean, I don't have anything against it. Dictere. Is that the Latin word? Against dictere, contradiction, contradictere. My Latin does not go very deep. Nobody knows. I can say that. Nobody knows Latin anymore. Now, this logical LaTeF is able to express the following 6 scenarios now. Now I can say A holds, there is evidence that A is true. A does not hold, there is no evidence that A is true. Negation of A holds, there is evidence that A is false. A does not hold, negation of A does not hold, there is no evidence that A is false. And then, when this consistent holds, I can say consistent A and A, there is conclusive evidence for A being true. Consistent A and not A, there is conclusive evidence for A being false. So let F has no theorems of the form consistency A. I mean, I can never prove that something is consistent just by means of logic. I need external information. I need a testimony, not for somebody, for something, for a theory, for a person that has seen the crime or whatever. Declaring conclusive evidence for A is not a test of logic, right? That's, again, replies to your question. So the Belknap epistemic says the following, and everybody, I think many people know that. T just told the true, F just told the false, known told neither true nor false, both told both true and false. So that's the interpretation of Belknap, 1977, page 11. The above four scenarios clearly correspond to the four scenarios of positive and negative evidence, but then the logic LF is able to express the fourth scenario plus two, consistent or classic scenarios in which contradiction and incompleteness are not allowed. Okay, so we are sort of enlarging this four-sided scenario of Belknap now by our six-sided scenario. Properties of this FD and LEDF, they're reflexive, monotonic, intransitive, compactive, as well, sorry. This is property of the direct consequence of the definition of deduction from premises, blah, blah, blah. So this is customary tasks in logic. I mean, easy to prove in general, but important for you to make it to have clearly what's the personality of the logic you have in front of you.
Walter, could I observe for the students, we are dealing with several consistent non-classical logics, well, so-called non-classical logics, but observe that the consequence operator is Tarskian.
Yeah.
It's
Well,
classical from
yes,
certain point of
yes.
view.
To be Tarskian, it needs something else to be have a finite character, to be closer to substitution. But yes,
Yeah, it's an observation because in general the consequence operator underlying or related to the logics we are studying is Tarskian.
Yeah.
Not non-monotonic or.
Yeah, but also monotonicity is an important property, and sometimes it's good not to have it. Usually in artificial intelligence, because of that, it's good not to have monotonicity. Okay? Modus ponens and deduction theorem do not hold as, in general, but an implication can be defined like in not A or B. Remember that we don't have implication, but we can define one. But then deductive syllogism is not valid. This deduction theorem does not hold because it's not the case that gamma A implies B implies not A or B, blah, blah, blah. But however, the following form of deduction theorem holds. If you add the consistency, then consistency of A and A entails B implies that consistency of A implies not A or B. So in the presence of this consistent operator, this not A or B gets back its character of implication. Okay? Valuation semantics, blah, 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 is very much normal as we would have to expect it. The only distinction is that if consistent of A is 1, then V of A is 1, then if and only if not A is 0. I mean, in the presence, if this guy holds the value 1, then we get back that negation and is if and only if. Negation is 0, if and only if, without positive 1 is 1. I mean, that's the only distinction here. And observe is this then, if then, is not if and only if. The second part is if and only if, and the first part is if. So, clauses 1 to 5 give evaluation semantics for FDE. If you stop it here, you have a perfect good valuation for FDE. 1 to 6 give up them to let F, and then we can prove that this semantic is sound and complete, and it has also a quasi-matrix procedure. But this can be understood in the following sense. So why P and not P implies Q is invalid in FDE, or in a LaTeX. Because if I have P is 0, not P can be branched here, 0 or 1. Okay? And then I add all possibilities of Q here. Q independently can be 0, 1, 0, 1, 0, 1, 0, 1. That's independent line. And then I come here and see, okay, 0, not P, by V1 I get 0, by V2, blah, 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 blah. By this number, valuation 7, I get the following. P dot P is 1 and Q is 0. Okay? So I have a counter model. He's giving me a counter model. This is, this kind of quasi-matrix has been introduced by Costa and Elias Alves years ago, and it has been repeated and found many times. It's a kind of non-deterministic semantics as well. It can be regarded to a possible translation if you like. So many combinatorial configurations do the same trick again and again. The semantic is not compositional, right? The semantic value of not A does not depend on the semantic value of the A. The meaning is already explained by a compositional inferential semantic that takes positive and negative evidence for propositional language as primitive, as we explained in a paper with Apilio Rodriguez, who is here and can correct me. But that's not a point here. That's some little points on proof theory and theory of semantics for logics. Again, we can prove that if P is consistent, then I reestablish P or not P. I mean, for consistent proof, I establish a determinational doctrine, going again to this square of everything. I call it the square of everything, not the square of a position, because it's universal square. That's what Marcus gave here. Well, okay, that only means that by adding, I have this procedure, it's decidable, okay? So this logic is decidable, I can decide it by these quasi-matrices, because they are always finite, they are finite objects, they are a bit less efficient, but then Alejandro can help me here, a little bit less efficient than classical logic, but I think they stay on NP completeness as well, right? They go beyond that. Now, an important and interesting point, there is a cryptic semantics for this logic. Very nice cryptic semantics. Nice cryptic style models for logic of evidence and truth can be defined and can be used to mold information storage, revisiting, revising, and retrieval. I show you how. Recall that F is an extension of the E equipped with both classicality operator and non-classicality operator, dual to it. As explained, let F is a paraconsistent and complete logic that extend, if it is a paraconsistent logic, that extend this, that one S missing here to be completely grammatically correct. That extend the logic of first degree entailment with a classicality operator that covers classical logic, and it deals with positive and negative evidence. We can be conclusive and non-conclusive. That's the whole story. Positive and negative evidence that can be either conclusive or not conclusive. If they are conclusive, we declare it to be true. That's the idea. So conclusive evidence is subject to classical logic, and non-conclusive is paraconsistent and paracomplete reasoning. In this way, let F is logical, formal, inconsistent, and undeterminedness at the same time. It's an LFU, right? Or LFIU, I don't know how to say it. LFU or LFIU? Okay, LFIU. Okay. So, okay, conclusive evidence is, I said, is subject to classical logic, and so when this consistent holds, A is treated as true or false by the formal system. Thus, while A and not A does not imply B, in this logic it holds, again, as I said, this gentle explosion consists of A and not A implies B, which means that conflict evidence cannot be conclusive on pain of triviality, right? So conclusive evidence cannot be contradictory, cannot be conflicting. Now, the cryptic models are the following. The idea is as time passes, suppose that a database receives information from different sources, reliable or unreliable. Its stage W represents one of the following scenarios. When W does not entail consistent of A, when it's not the case, that the world entails or infers consistent of A, then I can have W entails A and W does not entail not A. And the database has only information that A is true. Again, just the opposite here, does not entail A and entails not A. Database has information that A is false. Entails A and entails not A. Database has conflicting information. Does not entail A and neither not A. Has no information about it. So that's the 4 scenarios again. But then, completing the 6 scenarios, when W entails A is consistent, then W entails A, and now the database has reliable information that A is true, or the contrary, not the A, has reliable information that A is false. So again, we are restoring in this cryptic semantics our 6 scenarios here. So this, I tried to make a figure with 6 scenarios, which did not come out very beautiful. But again, I tell you something, I hate diagrams. I hate drawing because I never understand that. So I do this for the peace of mind of other people. So please read it if you like. I did it myself and I don't like it. I prefer the written information. But anyway, this diagram here, Abino likes it, does the same information, gives the same information as we had before. Now, how these cryptic models work is a non-empty set of states, and the accessibility relation is just a partial order. It's just a partial order. So I have this goes to L1 times W in language in words go to 0, 1, its evaluation function satisfies the following. So A and B holds at the word W, it's 1 if and only if it's 1 and B is 1. So conjunction, disjunction, blah, 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 is more or less the same here. So now number 6 is more complicated. Consistent of A holds in a word W, gets value 1, only if exactly one of the following conditions obtained. For every W prime, and bigger in this partial relation, bigger than W, VA W prime is 1 and not A is 0. So in the future, right? Or WA for bigger than W is 0 and not A is 1. So I have here some, this gives me information about the future in a sense. Because I can think of an instance of time, growing and receiving more information. And this is here.
Okay, why do you have only a rule for double elimination of negation, the rule 3, and not a rule for...
Because it's an only if. It's only if and only
okay.
if. Yeah, it's sufficient.
No, the question is that you don't have a rule for V, not A. But João Marcos told me that you have rules 4 and 6 that place that rule.
What did it say?
The one that you don't have is negation of the whole, but you have negation of all the other formats or the shapes. Negation of negation, negation of conjunction, negation of
Yeah. Okay.
negation of white ball is the dark ball.
So valid and semantic consequence given a cryptic model like that, and a stage W, a formula holds if you want, if and only if, blah blah blah. Semantic consequence, not the closest six of the definition gives only a necessary condition for this white ball here, V1. This mimic the clause for consistent of non-deterministic evaluation semantics. So, of course, we are replying here the evaluation semantics we had before. We have to be faithful to our previous semantics. So, that F can be proved to be sound and complete with respect to such cryptic models. Not any novelty here, so it's more or less expected. But there's some nice other points to be informed about that. Now, putting the database to work, how can we really use this model in a database? As I said, putting the database to work, persistent condition as policies of information update. To be used, therefore, from the point of view of treating information, we have to seek in updating databases in an automatic and formally correct manner. So the models of LabDev can thus be classified according to whether or not they satisfy one of the following persistent conditions. So how I can really use and can store information in an automatic way using this logic. So the three ways of revising the persistent conditions, I have P1 here, total non-revisability. For every W prime bigger than W, if it is 1, then forever it's 1. So it's non-revisability. It stays there forever. One way of using this model. You know what? But look, this is not part of the semantics. This is part of the way you'll be using semantics. You have to declare it. You have to add these conditions. So you can add this total non-revisability or P2, non-revisability of reliable information for every W prime bigger than W if A consistent of A in the order W is 1, then forever is 1. This is equivalent to a second form of a P2. The P2 line which says the following. Equivalently, if inconsistency in a W prime, posterior W prime is 1, then forever W less than W1 was 1 again. So P2 prime says that if some information is unreliable at the stage W prime, it had been unreliable in previous stages. Okay? So then the second condition is you only revise reliable information. And then no revisability of reliable information and basic information. Okay? If W prime is blah blah blah, then if it is 1 here at the W, it's 1 forever for consistency. For P, if it's 1, it's 1 forever. Forever bigger stages, later stages W prime. And negation is 1, then it's always 1. So you have 3 policies of using this database. Which one is more useful? I think it's P2 and P2 line. The best persistent condition. So condition P1 means total non-revisability. It states that if no information whatever is allowed to be revised at the end stage, in other words, every new piece of information acquired at a certain stage is always passing on to subsequent stages, leaving no room for data to be removed in light of new information. Okay, very rigid, quite rigid. P1 does not quite fit for the intended interpretation of that. This is because if I get inconsistent information from outside, they have to persist across the stage, we prevent it from acquiring reliable information. But what surprises that soundness and completeness we continue to hold with respect to classes of models corresponding to each of the persistent clause, P1, P3, whatever the other clause is. Which one do we choose? This must come from an external source, the designer. The designer has to decide which policy he is going to add to this logic. Okay? I would add P2 line, or P2, which is the best more. Okay, now going to this probabilistic semantics.
It's a question.
Excuse me.
Yes.
In the P2, it seems like you can't revise the information that A is consistent, but you can change like what the value of A specifically is. Isn't that a problem? Because you can you maintain that A is the information that we have regarding to A is reliable, but we don't maintain that reliably true or reliably false. Seems like you can change that, can't you?
It can, yes, yeah. You could, I mean, you say I can never, if I understood you well, you said I can revise information about A and not A, but I cannot revise information about consistency of A.
Yeah.
You can. You can. Yes, you can. Because there's no syntax that prevents you from the A to have this ball on it. We could have added another to this logic, another condition, like consistent of consistent is the same as consistent, for instance. Two consistent, sort of to get back to one consistent, but we did not. So in principle, we are open to this possibility.
One question.
Yeah.
I'd like to ask about the consistency. When I see the rules, we can easily make the introduction for consistency. The reason why you don't use those things is that because of your view about the consistency is if when we have a consistency introduction rule for consistent concept, there is another problem in there. That is my question, because we easily can make those introductions.
If I understood well, the following is the following. So you cannot make a logical proof that something is consistent.
It doesn't
Never.
matter. He said that you could he said you could add rules for that effect.
And you will have another logic.
Yeah, it would be a different logic, but
It's not what he
in
wants.
this case here, it's very minimal in the sense that you cannot prove anything to be consistent. As Guido said, not even arithmetic. But then logic is not able to say anything about the consistency of the external world. You add that information in your database, in your hypothesis, in your suppositions, and then you work on it. But then if you want to change that, you would have to change the logic and build another one.
It is because I know weather phenomenon. It's not because when I see some two formulas, I can see that two formulas are consistent with each other. What you mean? I don't get aware about what you mean about we cannot talk about consistency.
I'm not sure I understood your question.
The logic.
I would say maybe.
use consistent formulas.
No, I didn't
May
understand.
I suggest one way of implementing what you said? Would you agree that if A is false, it's consistent?
Can be consistent. Yes.
So that would require you to extend your logic because you cannot prove it. That if A implies bottom, then A is consistent. You don't have that rule. You don't have
No.
rule for introduction of consistency.
No,
You
no,
could
no,
have
yeah,
it, as he's
yeah.
saying.
Yeah.
That's an extension
Yeah,
of your
yeah,
logic.
yeah. I could have.
That makes your basic
Yeah,
connected
yes,
and
yes.
standard connected.
Yeah, I could have. But we don't.
It's not what he wants.
Yes. Now, probabilistic semantics for that F is the following. Well, I'm not going to lose time on giving the sixth scenario again, but what I can tell you is the following. I can add the probability, and I tell you how we can add probability to this logic and to many other logics if you like, using a very simple trick. If you suppose you have added the probability already. Suppose you did it. So if probability of A above alpha less than 1 means that P of A plus P of A may be less or greater than 1, which means that the evidence available for A does not behave completely classically, because it would have to be 1 to be classical, in the sense that it may be contradictory or incomplete. So probability of above A being less than 1 signifies that your consistency is not taken to be completely classical. It has some problem in it. Which kind of problem? Either missing or contradictory. Okay? Missing or contradictory. If it is 1, then we restore this classical law of probability. P of A plus P of not A is 1, which means that evidence for available behaves classically. Does it mean it's true? No. It means it just behaves classically. Can be false. Okay? If probability of A equals probability of a consistent of A and A equal 1, then it's taken to be conclusively established as true. And then in this case, P of not A is 0. Mutatis mutandis for the other one. So, truth means what are requirements for truth in probabilistic terms? Probability of A being regarded as 1, probability go to 0 and 1, between 0 and 1, and consistent of A again equals 1, right? Notice that the statement P of consistent equals epsilon or P or whatever is to be read as expressing the degree to which the evidence of A is expected to behave classically, rather than a measure of evidence. It's not exactly the measure of evidence, but a measure of the classicality of evidence. Again, it's a measure of the classicality of it. Is there any question? No.
I do.
Oh, yes.
So why you didn't consider the case where P probability of white circle A is more than 1?
No, it cannot be more than 1.
Sorry?
Probability to go between 0 and 1. There's summing. The sum can be bigger than 1. They can sum. The sum of probability of A and B can be bigger than 1, but not probability of A.
Okay, could you tell me why?
Why?
Yeah.
Because I'm satisfied with the classical theory of probability. We take 0 between 0 and 1. I don't need to get beyond that.
Number between 0 and 1.
Yeah, I know, but I think that the cool point of this approach was like P plus probability A plus probability of A can be more than 1. So which means like you basically break into the new world of probability, which is like it doesn't have to be 0 and between 1, right? So then I'm like then that's the reason why I'm a little bit confused.
Okay, so let's say probability of A plus negation of A may be less or greater than 1.
Yes, yes.
The
Right.
sum.
Okay.
So this one is 0.7, this one is 0.8. So the sum is 1.5. But not each of them. They sum bigger than 1. That's normal. That happens in classical probability as well. Standard probability has a proper.
So there's special case which you
Not for negation. Not for negation, but for A and B, right?
So that's only case where you allow to probability bigger than 1.
Yeah. They sum bigger, more than 1, but each one of them is less than 1. Okay?
I have another question.
Yes.
So, in the first time, you consider P of A plus P of not A is less than 1. So this, maybe I'm not following well, but maybe this indicates me that the negation will be complete.
Yes.
Yes, yes, yes.
And the second item, probably of the consistency of A is 1. It does not imply that it is not complete.
Well, if it's less than 1 is paracomplete, it's bigger than 1 is paraconsistent.
Yes, if the probability that A is consistent is 1, I would conclude that P of A plus P of not A is less than or equal to 1, but not exactly.
Now, if it's exactly 1, if P of A, if P consistent of A is exactly 1, then I restore this law here. So
It's because
it
they're
gets-
connected as a double rule.
Yeah.
It restores both. It restores
Yeah.
classicality at once. It's neither part consistent nor part complete. It points out to classicality actually. It's reading as consistency, but putting your mind is reading it as classicality.
Yeah. Consistency here is understood as classicality. Behavior classical. Now, some probability function. Now the trick here. The trick here I can apply to many other. Yes, please.
Can we go back to the first
Yes.
slide? So as far as I understand what you're saying, you say that consistency of A is different for asserting A or not A. But like what? I don't understand what's the relationship between saying the probability of A is less than 1 and the probability of A. It should be different. Like
Now, suppose you have a missing information. Something is missing. I have a probability that this is my telephone. I recognize it is 0.1. And somebody says, no, Walter's telephone is blue. So it is, no, it's not, it's 0.3. So I have incomplete information about who is the owner of this telephone. Then the probability of A plus not A is less than 1. I have missing information. But suppose Jean-Marc says, no, it's 9.7% is Walter's. And Abílio says, no, it's 95% is mine. Then I have an excess of information, and the probability of A plus not A is bigger than 1. That's the idea. And if someone says, no, let's restore classicality. So this should be treated classically. Then probability of A plus not A is exactly 1.
But I don't understand what is the probability of the consistency of the.
Is how probable it is to be reliable. For instance, if Jean-Marc tells me something, I don't believe him. So I give him probability 0.5, that's what says it's true.
100% reliable, come on.
If Hitler says something to me, even less, sorry, more. Now, supposedly, depending on the source, I get different sources of information they have different degrees of reliability. Okay? That's why, different degrees of reliability. So, the trick for assigning probability for almost every logic is the following. Now, if I have time, I'd like to talk a little bit about the difference between probabilities made by engineers and physicists and mathematicians and probability made by philosophers. Probability by mathematicians, engineers, and etc. They use statistics, they talk about events. They talk about a omega algebra, right? They talk about a kind of a Boolean algebra with some kind of operators. And they regard the probability as a kind of mathematical theory as much as very close to what topology is. Very much to what topology is for them. But here, probability for philosophers, that's what we're doing here, is completely different. We assign probability to sentences in a logic. So my trick here is to assign probability to any other logics, other than classical logic. So how I do that? So first action, non-negativity. So probability goes from 0 to 1. I don't need them to be bigger than 1. I could be, but I don't need them. It's sufficient to be close to what mathematicians do. If I have anti-tautologicity action, if A is a bottom particle, probability of A is 0. If A derives everything, probability is 0. I don't say if it's false, if it's the bottom particle. Comparison. If A entails B, probability of A is less than probability of B. And finite additivity, because this reflects the behavior of conjunction and disjunction. Probability of A or B is A plus B minus the conjunction. This is a combinatorial property related to positive conjunction or disjunction. And the important one, I add here the following. I don't need that, I can derive that. If the probability of alpha is less than probability of, consists of alpha, less than alpha plus negation of alpha, less or equal than 2 minus probability of consistent A. No, I don't need this fifth axiom here, just put it here to, I can derive it to show you that we get some strange properties. The axiom, if A is a tautology, if I prove A, then the probability of A1 is not necessary because F does not have a tautology. But if it has tautology, if a logic has tautology, just add that. For the majority of logic is even Lukashevich logic, LF, I1, blah, 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 many other logics, you can get the probability attached to it. So, yes.
Sorry. I probably mixed up PLD and left F.
Yeah.
But you don't need the condition 2 then. You also don't have.
I don't need what?
Condition 2, go back, please.
Condition 2.
Yeah, you go back one slide. Yes. You don't have bottom particles. You don't have tautologies, and you also don't have bottom particles. Right.
Yeah. In this logic. But in LATF, I do have it. I do have it.
You just said that in LATF you don't have tautologies, but LATF is the one with implication, right?
No.
No?
I can restore implication, defining not A or B.
Either
If
you
A
have,
is
either you have
consistent.
both or you have neither.
Hmm?
If you don't have tautologies, you don't have the border particle either. Either you have both or neither. So you have to decide, make up your mind, what's the logic you're talking about here.
I do have bottom particle. don't I?
So you do have
Yes.
tautologies too, it's the negation.
My assistant will reply to this.
FDE has no tautology, but let F has tautologies and has bottom particle. A tautology of let F is white ball, disjunction, black ball.
He just said that it doesn't have
Yeah,
tautology.
Yeah. Okay.
It
That's the
should
wrong
be
sentence.
FDE there. FDE there, not
Oh,
let F.
last line.
That axiom is not necessary for FDE.
The last one should have the
Mhm.
FD.
This is the
For
price you
let
pay
F
for
is
using
not
all the slides.
Yes. You mix it, the slide of
Yeah,
FDE
yeah.
with the slide for.
You know,
let F.
giving a talk is no thing. Writing slides is everything. I suppose you know that. Okay. Anyway, important point here is that I can prove the a kind of probability completeness for this logic here, right? I can prove that I not only have this semantical completeness, I also have this probabilistic completeness, which means that my way of defining probability is tight enough, is very well suited, right, for this. I'm not exaggerating any property here. So it's a second way of proving completeness for this logic. It has 50 minutes. So, in other words, you can think about probabilistic completeness as in such a way that the 0-1 is this 0-1 completeness, this usual semantical completeness, is a particular case of crazy probabilities which always take 0 or 1. Degenerated probabilities. So, if you have a probability completeness, usual semantical completeness is a subcase where probabilities are generated. So you don't need them. You have one of them, you get another one. Okay. Now, some properties of let F. Let's forget FD for a moment. Holds the probability interpretation like that. So, I can have many other properties that I don't have in a classical case, but I go to more interesting things. Independency and incompatibility. A and B are said to be independent if P A or B is the product of PA and PB. A are incompatible if PDA and B is a bottom particle. Incompatibility implies dependency, blah, blah, blah. So some properties that show only that from outside the formal system, it's expected that as the value of the consistency of A increases, the dependency between A and not A decreases. The formal system alone, however, is not able to fully express this idea. Dependence in classical probability, A and not A are completely independent. Here, by this notion of dependence, they are dependent, and they get more and more independent as the probability of the consistency of A increases. Okay. Some facts. Some important point here is some total probability theorems can be established for propositions that behave classically. If the probability of consistency of A is 1, then P of B is conditional probability B given A times multiplied by PDA plus probability of PDB given not A multiplied by P of not A. Then it holds if this probability is 1. So what is the conditional probability? It's the same as the classical one. Probability of conditional probability of B given A is the probability of B and A divided by probability of A. Okay, I could add here a new way of defining conditional probability, as for instance, as Karl Popper does in his treatment of the probability. He sort of solves this famous problem of the zero denominator, which says the definition of conditional probability only holds if P of A is not zero, right? By using Popper's, we can avoid that problem, but we didn't do that for the moment. We stayed with the already classical definition of conditional probability, which is already sufficient for our case. But if you have this total probability theorems, we can make some applications, and we can think of the standard Bayes rule, and we can think of extending Bayes rule. This is a very important point, which I'm going to talk more and more in my last lecture here, by the end of this school. What is important here is the following. You know, standard Bayes rule is kind of a very stupid little theorem with lots of incredible consequences. It's very simple to be proven. You can, if you take the definition of P of alpha given beta and P of beta given alpha, you just define it in probability of the conjunction divided by P beta, and here's probability of the conjunction divided by P of alpha. You compare them using a high school trick, you just cross, and you prove that P of A given alpha given beta is the probability of beta given alpha multiplied by probability of alpha divided by P of beta. In terms of measure of evidence, probability of beta given alpha is called the likelihood, is the evidence for beta given when alpha is given, and two versions of the Bayes rule can be defined here in this logic. One of them, and this is, according to my point, a revolutionary point. I'm sorry to say to you that I'm very much excited with exactly this point here, applying new forms of Bayes theory. This is very much interesting for my view. By the way, Juliana Bueno Soler and myself, we won the Costa Prize exactly with this idea, right? Claiming that claiming that Bayesian epistemology can be revised in terms of paraconsistency. Then we introduced the so-called paraconsistent Bayesian probability. Some other people have thought about that. I mean, I think Graham Priest had already proposed that in a paper long ago, some way of doing that. He said, well, we don't need to stick to stay. We don't need to fix the ideas that class probability is the only one possibility. I think you said that, but now here we are sort of reworking everything in a way using our logics, not the other logics, and in a way that can be used, can be useful. Then the Bayes conditionalization, thank you. The Bayes conditionalization rule for LTF is the following. Negation BT. Why negation BT? Because I have this black ball BT. I have the negation and the inconsistent version of it. I just discussed with you the negation version. Negation BT, negation Bayes theorem. If for PA bigger than probability of A and not A, look, in classical logic that is always the case. If A is not zero, because probability of A not A is zero. But here, not necessarily, so if probability of A is bigger than the contradictoriness of A, and PDB is bigger than the contradictoriness of B, then probability, negation paraconsistent probability of B given A, revised by the information A, is exactly the probability of A given B, the counterfeit, multiplied by this distinction, by this difference here, divided by the difference. What am I doing here? Very simply discounting. Discounting. Just compare. I'm just discounting the degree of contrariness. Just a simple, stupid, silly idea, but it works very well. Why it works very well? Because then when a simple idea like that, you can work with contradictory proposition. I'll give you some examples in my last lecture. How can you really use it to obtain some very new conclusions that you could not do before? Okay. So, what do probabilities over let F represent? We can say that let F represents a nice new tool for reasoning. I like to say that. Let F represents a nice new tool for reasoning because we're talking about evidence and about the probability, about ways of measuring degrees of reliability of evidence. Now, evidence is not well treated by philosophers. Philosophers like to treat belief, knowledge, but no evidence. Very little work I can say about evidence. Probability and possibility measures, I can also define here possibility measures, which are not only for probability. Possibility is this line of work by Dubois and Prade in Toulouse. They have like almost 100 papers on this kind of possibility measures. We can, as well as using probability, we can attach possibility measures to such logics. And I have a paper on that published in this book by honor to Arno Avron with Juliana. New forms of Bayes' theorem. That's the important point. Can be developed for them and new forms of update. So I can update even in the presence of information that is not reliable, if I know the degree of reliability of them. Okay? This shows that probability goes hand in hand with logic, but not necessarily with classical logic, as some philosophers can. What are the connections between probability and logic? Much beyond the classical logic, as some philosophers like to say. And then there's lots of work to be done. Now, thank you very much for your attention.
It's really interesting by itself. This definition that you spoke about. But I don't quite get the grasp of the motivation behind it because we have lost the second converse action. Right?
We get closer because I did not get to what you did not get.
Oh, the motivation, because we have lost the second action of Commodore that is a negative one.
What's the second action you say?
The negative, the set of all the possible bands equals to the center. And we can always add more bands over omega. And we can cut the ways we can use and extend it without these things.
Well, because homography is connected to Boolean algebra, in a certain sense. I am not connected to Boolean algebra. So you say it is missing this action. It's not missing, it's hidden there. So I can have more. Like if, for instance, I can have P of A plus P of not A be bigger than 1. Homography cannot have that. You know? So I'm open to this. So I can sum more than homography can. That's all.
So you want to do more.
Yeah, I mean, I'm more flexible than homography.
You are extending.
Yeah, I mean, sort of extending. So if everything is consistent with white balls, I can get back to a form of a homography and probability as well. I'm just extending.
You said that we can add the probabilities of A and B and be bigger than 1.
Can be bigger than 1, yeah.
But in that case, what's the probability of the disjunction of A and B?
The disjunction is given by this axiom number. Disjunction and conjunction is very much complicated. Why? Let me show you why. Yeah, this finite additivity here. You know, this only says that Kolmogorov has also this finite additivity, and some other people, like I think is Alfred Delaney and other people, add to this an infinity additivity, right? Infinite additivity.
But the probability can be bigger than 1? Or they just
Not for them. For the classical case, it cannot be. Here,
but in yours.
in my case, well, it could be, no problem. If A or B. If B is not A, it can be bigger than 1.
But you said that it's not possible for a proposition to have a probability bigger than 1. Just
No. I mean, sorry. Okay, I mean P of A and P, the sum. This right side can be bigger. The right side.
right there.
Well, then you say, then A or B will be going to be bigger. No, then it cannot be. No, it cannot, but then it was implied. No. I mean, the problem here is not with arbitrary A's and B's. Is with A and not A. For positive logic, it's behaved like in the classical case. Just to reply to you in better terms. No, this right side cannot be bigger than 1, but because then PA or B would be bigger than 1. No. But I mean, what's important here is that P of A and P of not A, the sum of them can be bigger than 1.
Doesn't that case?
Yeah. But each one of them is less than 1. I mean, yes.
I just wanted to point out, I don't know who asked the first question. Yes, the second action, Kolmogorov action, is actually not broken because you still have the probability of the entire space is 1. I think there's been a confusion throughout the lecture that, okay, the sum of P of A and P of not A can be bigger than 1, but that's not the P of the union of the facts. Because here we have a per-consistent environment, and then the sum of the intersection of the two events can have a positive probability.
Yeah.
And then the second action is still valid, as far as I can tell. It's just a small confusion.
Yeah, but let me tell you something. I cannot really think about sets here. There is a distinction between philosophers' probability and physicians' probability, mathematicians' probability, right? They think about sets all the time. We don't have here a universe of sets, and we don't need it. We are doing probability directly connected to logic. We don't need to pass through sets and through Stone representation theorem. No?
No, I just mentioned sets because it's easier to think about probabilities using
It's easier,
sets.
yes, it's easier, but it's very hard because they don't give you the right picture.
The right interpretation.
Yes,
In this setting, which
Yes.
is broader.
Yes. Yeah. For instance, using this RMBC logic that Marcelo and I propose, we can algebraize para consistent logic, have an algebra, and redo everything. Yes, please.
Faz a diferença ao compares. Isso é o que a gente foi dizendo. É aquela relação de consequência na classe.
Yeah, Bilo is pointing to fine. Comparison here is very much important because this consequential relation is not the classical one. This consequential relation is not the classical one. If you want to connect it to the logic.
No, yes.
See?
Okay.
I have a question. Early on in the talk, you mentioned that you may have evidence for A, we have evidence for negation. And most accounts of evidence, that means that we really don't have the evidence. Now my question to you, of course, we may be in a quite consistent setting that we change the situation, but the question is your intention to capture kind of normative account of evidence? Or are you trying to replicate ways of the way that people reason about evidence.
Second case.
The-
Second case, yeah. Not the normative, that's the descriptive way.
Yeah,
Agreeing to what people say.
yeah, but people reason very badly.
Well, I mean, listening to the people that reason well. You know, in a certain sense, I'm not trying to give some rules that people have to follow. I'm trying to capture, as people do in logic, right? As people do in first order logic, they try to capture the way people think with quantifier.
Yeah, but they capture validity. They want to capture proper, valid inferences, not that ones.
It's very hard to say if I am being normative or prescriptive here. I prefer not to be normative. I prefer to be prescriptive in the way, I mean, civilized and intelligent people think about evidence. But I really don't know the answer to your question.
Yeah, thank you.
I really don't know. Yes. Yes.
Thank you for the lecture. My question is kind of related to that of Xavier.
Uh-huh.
So if you want to capture how we reason about evidence, and you had this motivational case, for example, two tests for a disease, right? Where one is positive and the other is negative. So in this situation, we have some evidence for A and some evidence for not A, but intuitively, it does not seem to be the case that we have evidence for A and not A. So intuitively, we do not have evidence for the case that I am diseased and I am not diseased. So this is at least from my point of view. So I wanted to ask, what do you think about that introduction?
Okay, this depends on whether you are adjunctivist or not adjunctivist, right? I mean, if you, Prisha said that, mentioned that, or people mentioned that as well. So this is the difference between being adjunctivist or not adjunctivist. As Jaskowski, for instance, was not adjunctivist. He said, I can believe in A and B and not believe in the conjunction of A and B. Here, I am adjunctivist. I mean, I believe in A and I believe in not A, and I believe in the conjunction of both of them with a certain degree.
Well, but if I understood well, you want to, I mean, according to your position, like ontology is consistent, right? So there are no true contradictions. Is that okay?
I don't know if there are true contradictions or not. I don't need to take them into account. There may be. I don't know. There may be.
Fair enough.
There may be. I'm more concerned with contradictory information, belief, dreams, language, blah, blah, blah. Are there real contradictions? Are there real deleterious? There may be. Nothing against it. It would be it's a nice position. Yeah.
My question is about the second to last slide. You go there.
Which one?
Second to last.
Second slide.
Second to last.
I didn't understand which one. Ah. So this is the last one? And before, is it?
Yeah, yeah.
Okay, sorry.
The last expression. I mean, correct it if I'm wrong, but when you're doing the probability of the conjunction of A and not A, you're kind of trying to find out the corrupted part of the probability, right? Part that
Yeah, I'm sort of discounting, yeah.
Yeah, the part that does not allow you to be classified, right? But I mean, why do you subtract it entirely from the probability of B? Why do you don't like subtract just half of it from the probability of B and the other half from the probability of not B? You know what I mean?
Well, could be. That's why it would be another form, even a third form or fourth form of a Bayes conditionalization rule. So we may have several forms of Bayes rule.
Yeah,
Because that reflects the way you are revising your knowledge. So you are proposing to revise my knowledge, taking into account that half of it is go on one side, half of it go to another side. Could be. Could be defined that way. I did not. But it could be. The problem is to find good applications for it. I have a moment application for this way of thinking. The way you propose is new and interesting, but first of all, it will be formalized. I don't know how I formalize half of it. It's hard to say, right? Divided by 2.
I just asked because that part seems a little bit arbitrary. You know, you can amount the conjunction to either side.
Yes, you are right. It would be more democratic to think that, okay, you treat contradictions in a more friendly way, and not just subtract part of it. Okay? But then, even being non-democratic as this here, you already have nice and new applications. So, proposing what you say would be nice. I don't know how to do that. How to subtract part of the contradiction only.
It's good from both sides, right?
Yeah, maybe, I don't know, half of it. Then I have to say, maybe 80%, 20%, how much, right? Yeah, it would be a nice idea, but we did not try yet. Thanks for the proposal. Would be nice. There are more questions, yes. Yeah.
But I guess so. But the mathematical proof is of a completely different nature. So I was asking, so if this is what you told us, that para consistency might not be adequate for mathematics. And if this is so do you think that para consistent mathematics is some kind of indesign?
It's a kind of what?
Of no way,
I really don't know that. But it depends on what you want to do with mathematics. For instance, mathematicians invent things when they need it. Or sometimes they invent it because they don't need it, and later on they find a way to use it. But at this moment, they did not find, as far as I know, a way of really inventing new mathematics. You can have new forms of set theory, blah, 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 but you don't have new forms of proving theorems, for instance. Like I almost proved that theorem, but not yet fully completed. I don't know, the future will say. I think at the moment, mathematicians, as they are, they don't care about any form of non-classical logic using mathematics. They don't need it. If they ever need it, then there will be an explosion.
But what about intuitionism?
Do any mathematicians pay attention to intuition?
Yeah.
You believe it?
Supposedly there are.
They don't care.
There are some books.
Huh?
There are books.
You know how mathematicians work? When they try to find to give me a counterexample, they demand for you a constructive counterexample. When they are in their house preparing theorems on paper, they are formalists. On the way promenading in the park, they are Platonists. But when they require your counterexample, then they require you to be constructive.
Walter, do you remember when Newton da Costa once told us that when he was a student in Curitiba at the Federal University of Paraná, one of his teachers proved something, and Newton said, "But this is wrong." The professor said, "Why is it wrong?" Newton went to the blackboard and showed him a counterexample.
Counterexample, yeah.
And the teacher said, "No, in this case, a counterexample is not sufficient."
Yeah. Just one counterexample. What are you thinking? You're crazy. It's one. Lots of nice examples. Just one counterexample. Anyway, any more questions? Any more comments? So thanks very much.
Let me thank João Marcos and Walter for this so beautiful course.